All right, well, thank you very much. My name is George Porter. I'm a researcher over in the computer science department. And actually, this talk was put together by my student, Mike Conley, who's unfortunately developed the flu over the weekend. So if you're looking for big data problems, I recommend curing the common cold. That would be very, very helpful. So I'm going to be talking about a system called Themis that we built at at the CS department. And we're interested in all of the same things that people in this room are interested in. So efficient big data processing of very large data sets. And so we're talking about hundreds of terabytes, petabytes of data spread across many different kinds of services. And we're interested in things that are manipulating that data, doing transformation and aggregation. And specifically, we're really interested in looking at things that are streaming through a lot of data, looking for a small amount of results. And so these are workloads that require a lot of I/O, but not necessarily a lot of computing. And we're really interested in building systems that are very efficient. And so we've been looking at this problem, as of many other people. And I think the big thing that we've been trying to do is really not only build software systems that are designed to be efficient in terms of I/O, but also trying to just really explore how to build large parallel processing systems. And so I'm going to be talking about the system we call Themis. And I want to point out that what we built is a large MapReduce system. And you're probably familiar with MapReduce through things like Hadoop. And Hadoop's actually a really miraculous piece of software because it's very, very scalable. It's been used in a lot of different successful deployments of big data processing. But if you actually zoom in on what a specific node is doing in one of these very large scalable clusters, you'll see that actually it's not doing a lot. There's a big gap between what a modern server can accomplish in terms of data processing and what it ends up accomplishing inside of the context of this Hadoop system. And although you end up getting very large aggregate performance because it's very scalable, you're actually leaving a lot of performance on the floor. And so we kind of looked at trying to solve this problem from a couple different angles. And so we built this system called Themis, which is our own implementation of MapReduce. And we really decided to focus in this particular project on trying to squeeze out as much performance as we could get from our storage system and from our underlying hardware. And for this community, I want to talk a little bit about our system, but the big message I want to put together is for those of you who are building these very large big data clusters, maybe if you're a biologist or you're in a field that where you're trying to start sourcing a hardware to build a cluster, it's really important not just to look at the capacity requirements that you need and the programming model that you need, but you actually need to architect your hardware and software from the start to support parallel I/O, because that's really the only way that you're going to be able to suck enough data in to make full use of it. I mean, if you look at the components that exist in systems today, we've got really beefy processors that can support tens of gigabytes a second of data, memory modules that can be stacked multiple deep. But when you look at things like the network and the disk, what you're seeing is that the actual bandwidth that these deliver has not kept pace with some of these other components. And so even though I can stack 16 or 32 cores in a machine, put a ton of memory in there, the disks that actually hold a lot of the source data, the intermediate data, and the output data, as well as the network, don't scale in the same way. And so they oftentimes can become the bottleneck. And so that's really the bottleneck that we focused at optimizing in our system. And so we have this hardware design where we decided to really design for I/O bandwidth. And so we built a cluster that can support 300 terabytes of storage. But we actually ended up constructing it as a wall of disks. So we have about an order of magnitude more disks than we need if you were just looking at it in terms of capacity. Because what we really cared about was parallelizing tasks across that to deliver a ton of bandwidth. And the software that we designed differs a little bit from Hadoop in that we tried to fully extract as much bandwidth from this thing as possible. And what I mean by that, so we had this NSF grant, this MRI, to build one of these clusters, and it's over in the Cal IT building, and you can take a look at it if you'd like. And again, it's one of these, there's a couple other racks that aren't shown in this picture, but it's basically a wall of disks. And the main insight that we had when we designed this Themis system is that if there's this theoretical result that shows that MapReduce-like systems that are built on top of sorting as a kernel of processing require at least 2 manipulations of every data item in the worst case. So in order to sort data, you basically have to touch it at least twice, both reading and writing. And we kind of say that any system that meets that minimum lower bound has this 2IO property. And the way that systems like Hadoop and others are structured, it's oftentimes the case that depending on the way your cluster's built and depending on your jobs, you may end up manipulating data items many more than that minimum of 2 requirements. And so a lot of inefficiency stems from the fact that you end up reading and writing data multiple times. And so we tried to design this Themis system so that we actually meet this 2IO property in the worst case. And so instead of having a job, a big data processing job, subdivided into many, many tasks. Instead, we have two phases of operation. And so we end up mapping and shuffling all of the data in one phase. And then we have a second phase that sorts it and then applies that aggregation function, that reduce function. And this isn't necessarily appropriate for every type of job, but for very large jobs that deal with hundreds of terabytes, it actually ends up being a quite efficient way of doing this kind of processing. And so we took this system and we were interested in some way to evaluate it. And since we didn't have Google's traces and that kind of thing, we decided to participate in this annual sorting competition that the late Jim Gray created in the 80s to sort as much data as you can. And so there's this challenge to sort 100 terabytes of data, and we went ahead and entered it. And this graph shows some of the results. And on the y-axis, you can see the total amount of data that was sorted via MapReduce. And on the x-axis, you see a couple different instantiations of this annual competition. And when we started, Hadoop, run by Yahoo, was the had the world record in sorting at about a half of a terabyte a minute over 100 terabytes. And our system that we built with that equipment from CaliT was able to beat that by about 20% or so. So we were able to sort data through MapReduce faster than Hadoop was. Of course, things change. There's a lot of competition, and so Hadoop ended up retaking this record back from us, and they're performing about half as fast on top of us as we were. But what I want to point out is that if you actually look at the per node efficiency, you see a kind of a different story. So in this graph, what you see is on the y-axis, it's the cluster size. So it's how big, how many nodes, how many servers did you need to actually achieve this goal? And originally, Hadoop was using about 3,500 nodes. We used about 45 nodes, and then they've retaken us again about half as fast as we are with about 2,000 nodes. Now, again, I want to kind of emphasize that one of the advantages of our system is that for single jobs that are very, very large, you get a lot of efficiency, but you don't get a lot of statistical multiplexing. But I kind of feel like for the audience in this room, a lot of the kind of jobs that you're interested in are, in fact, these very large single jobs. So it's not that you necessarily have thousands of jobs that you want to run on a cluster and get a lot of statistical multiplexing. Rather, you might have a very large sample from some sort of biological application or a very large piece of data from an archaeological site, and you want to process that independent of other jobs. And if you find yourself in that type of situation, please come and talk to us, because I think that some of the techniques that we've been exploring might be useful for you. So I think the key takeaway is that the programming model that you use and the cluster size is not enough. You really need a lot of parallel I/O, and we're looking for data-intensive problems that meet this particular structure. And with that, I'll turn it over to questions.
All right, thanks, George. I realize I have too few hard disks in my workstation upstairs.
Yeah.
Any questions? We have one here.
So this is on?
Mm-hmm.
How much of the advantage that you're getting is in software versus hardware? And the reason why I'm asking is that for some of us, we can't afford to run the way that you run. Mm-hmm. And we have to, because of capacity, go to the 4 terabyte disks. Mm-hmm. And so...
Yeah, so that's a great question. So the question, I guess, was sort of how much of this is software, how much of this is hardware? And ultimately, the answer is you really have to co-design the two if you want to get a ton of throughput. So our system is about 15% slower than the raw underlying capacity of our hardware, meaning that there's about a 15% or so gap between what the hardware is capable of performing and what our software can do. And if you end up architecting a system with much fewer drives, I think what you would find is that your CPU would end up being idle, and your network would probably be idle. So it's ultimately a cost trade-off. If you have the time, you could use a cheaper cluster, jobs run longer. It's sort of, at the end of the day, it depends on what your model is. If you have a ton of data that you want to pipe through it and get kind of economies of scale, it may be better to buy a more expensive interconnect and a more expensive cluster and amortize that over more users. But it just depends on, you'll have to work it out in a spreadsheet ultimately.
All right, we have another question over here.
Yeah, so for if you wanted to run a really large task and you wanted to run it maybe like once every 15 minutes, all day, every day, obviously with Hadoop, it's going to be cost prohibitive, especially with when you're showing like 2,000 servers.
Yeah, so Yahoo is using 3,500 or 2,000.
Right, and so what, do you have sort of the cost ramifications for using Themis instead of that solution? I mean, how does it, is there like an example off the top of your head?
I think the question's about kind of if you have these intermittent, iterative type jobs, how does the cost scaling work out? I think, so in just talking to some of the people who run at least online sort of internet data centers, it doesn't seem as much that you have these multi-petabyte jobs that you end up running iteratively. Rather, a lot of times you end up taking small additions of data, maybe click stream data that's arriving every 5 minutes or something like that. And so usually you tend to see these long tail distributions of data size where there might be a couple jobs that do run for tens of hours. But then there might be thousands of these little tiny jobs that run kind of iteratively. The one thing I would say though is that there's been a lot of recent work on doing things entirely in memory. If you have kind of small data where you can fit the data in the DRAM of the machine, that's the way to go. But they're just, at the head of that tail are these huge jobs, and they just take a lot of machines, a lot of hours to process. And so I think for those type of jobs, optimizing the I/O path is the best way to get cost savings.